since the first, well, since the third or something like this.
And he will talk about diameters of transportation and network flow for space.
Thank you. And some other polytopes. So Sangil, thank you for the invitation to come here. It's less than 2 weeks that I'm here, and it's nice to have some interaction with people already at another school. What I'm going to do is talk about transportation and network flow polytopes, talk about some of this stuff in the context of some other polytopes. The questions that we're going to be dealing with are the diameter or the Hirsch conjecture. If you've been around sometime in the afternoon, that it's been sort of the focus of a lot of the things I've already talked about. But if you missed all that, I think all the details are in here. So you don't have to be confused, and you can, of course, ask questions. So before I go too far, I want to say that some of the work in here is joint with Henning Glenn Fujimoto, Jesus Antonio de Loera, Shmuel On, Vincent Pilot, and Francisco Santos. And I also report on some independent but similar work by Lane Stauchi. Okay, so what I want to do is talk about the Hirsch conjecture, what it is, why we care about it, why we care about some variants of it now, and what we are going to try to do about it, and the history of it, so that some of the context of what I'm talking about makes sense. Then we're going to look at that conjecture, or some of its variants, if you will, for a certain class of polytopes. Right? So we're going to give up on the general problem and say, maybe this is too hard. What can we say about diameters of some families of polytopes? And then, in a sort of devilish last thing, what I'm going to do is kind of go back to the original question and talk about what do we have as means of attack. Okay, so that's the basic thing. So let's start with the Hirsch conjecture. So you start with a polytope. It's a d-dimensional polytope with n facets, and like this three-dimensional polytope you have here. Probably there's something like one big square-ish or parallelogram-ish thing in the trapezoid face in the back of this thing. So if that were true, then you see 1, 2, 3, 4, 5 plus 1, 6 facets on this three-dimensional polytope. And we're going to look at the graph of the polytope, or the one skeleton, right? So you have the vertices of the corners of the polytope become vertices of the graph, and then you have edges become edges. And we're going to focus on the diameter. That's what the conjecture asks.
So the back wasn't a trapezoid.
The back was indeed not a trapezoid. It turns out that it's a cone over this, well, yeah, so it's a bunch of triangles. Well, whatever. I did that so that the picture's slightly interesting. There's actually also a missing edge.
Okay.
If you notice that this one in the northwest corner is somewhere gone, right? So you'll forgive me because you're nice people. We're interested in looking at the diameter, which is the maximal, maximal minimal distance, whatever that means. So what I mean is, take two vertices, like the one highlighted here in red and the one in blue, and we're going to compute the distance for these two vertices. So the red and blue vertex are not directly connected by an edge, so their distance is not 1, but they do share a common neighbor, so their distance is 2. Right? And so you look at all the distances between all pairs of vertices, and that's the diameter. So for this particular polytope, is it 2 or is it 3? It's at least 2. Even with that edge added, I think it's still just 2. I don't think there's two vertices that are distance 3. Is that right? Yeah, I think so. Okay. If nobody spots that, then by majority vote, the diameter is going to be 2 for this. So the conjecture of Hirsch from 1957 is that the diameter is going to be no more than the number of facets minus the dimension. The original conjecture actually said kind of a little bit more, and it dealt with possibly unbounded polyhedra instead of just bounded polytopes. It dealt with doing some path that has to be monotone with respect to a given linear functional and all these kinds of things. It turns out a lot of these sort of more general formulations are actually false. And so this is sort of what has become the Hirsch conjecture lately. The reason why the conjecture looked like this is because of the relation of this thing to linear programming. Right? So in linear programming, one way to solve a linear program is by the simplex method, which You may have learned some really, really ugly formulas that you should forget if I were you. The simplex method is better described geometrically, right? It says you have a linear function, and you want to know which point in a polyhedron, or let's just for now stick to polytopes, which point in a polytope is going to maximize the value of this linear functional. And it turns out that one of the best answers you have is going to be at a vertex. So great, you'd think, all right, well, I'll just take my polytope, enumerate all the vertices, compute the value of this linear functional, and be done. But that would take too long, so the better thing to do is to use a simplex method. So you find one vertex by magic, and then you traverse along the graph of the polytope, which is why the Hirsch conjecture is important, right? From vertex to vertex, always increasing the value of your linear functional phi until you get to a maximal vertex. But it turns out for most of the rules that we have for deciding how you're going to go to the next better vertex, there's some kind of nasty polytope in the way, like what's called a Kleene-Mintz cube. Like that's like this thing over here. You might, for instance, end up starting at this vertex as being this magic vertex, or phase one vertex if you took a course in optimization. And you might have to trace some bad path that goes like this, and it is monotone with respect to the up linear functional. But there's maybe a better way to go from that initial starting vertex to your final vertex, right, in one step. So there's these questions of pivot rules that come into all this, and I don't want to get into so much of that. I just want to summarize by saying that the diameter is going to at least say this, right? It's going to say if you start at the furthest away initial vertex, then no matter which pivot rule you use, even if you use the thing that says just do what's best, do what's going to reduce the amount of steps you need, then you're going to need to take at least as many steps as the diameter of the polytope to get there. Okay, so that's why we're going to look at the diameter. So let's kind of go over some quick history of what happened with the Hirsch conjecture. And lately, Francisco Santos proved in May of last year that the conjecture is false. And if you were here about an hour ago, you heard exactly why that's the case. And so if this conjecture is false, you can ask the question, well, is the diameter going to be at least linear in n? N is the number of facets, right? And, well, we don't know. I mean, what we do know is that if you keep the dimension fixed, then the diameter is linear in n, right? I mean, there's some bound that looks something like, if you care, it looks something like 2 to the d minus 3 times n. Okay, so fix a dimension, or say I'm only looking at polytopes of dimension at most 10, and then you have some ugly constant in front, but then you have linear in the number of facets. So you have this question of is a diameter linear in n for all dimensions, right, uniformly in d? Okay, can you just get a formula that looks like delta is less than k times n? That's it. So that's still open. The best known upper bound we have is a really short paper due to Gil Kalai and Daniel Kleitman that says that the diameter is no more than roughly n to the log of the dimension. Okay, and if you don't know what to believe about the linear Hirsch conjecture, you could still at least be safe and ask, this what's now the so-called polynomial Hirsch conjecture. Is the diameter going to be just a polynomial in n? And again, here, if the dimension grows, then this is not a polynomial, right? Like every time the dimension hits another power of 2, then you've increased the exponent here. But can you make this thing a constant somehow? Okay, so those are sort of the relevant questions. And I should say that maybe these two questions, the linear Hirsch conjecture and the polynomial Hirsch conjecture, they're still kind of fair game to ask even if you deal with unbounded polyhedra. Okay? I'll just quickly give you the laundry list of when the Hirsch conjecture is known to hold. So it holds for 2- and 3-dimensional polytopes. It holds when the conjectured upper bound value is at most 5 initially and then recently improved to 6. So if the number of facets is not more than the dimension, then you have some, arguments of, well, there's only so many combinatorial types possible. Let's look at them, and yeah, these guys are all okay. Okay. This third one I don't really want to talk about, but there's some. You take transportation polytopes, which I'll define later, of course, and you take some kind of dual of it, not the one you're used to, and those polytopes satisfy the Hirsch conjecture. If every vertex of the polytope is a vertex of a cube, then the Hirsch conjecture is true for those polytopes. And there's some other small list of things, some of which you'll see in some later slides, but more or less this is the list for is the Hirsch conjecture true, and not some variant of it. Okay, like I said, I just briefly mentioned that this is the best known upper bound, and it's true not just for bounded polytopes, but for possibly unbounded polyhedra. And there's a larger class of objects where it's known to be true. These somehow some kind of abstract polytopes. They'll come back to this at the very end. Like this will come back up just for a moment. But you can ignore that until like the last slide or something. So that's kind of the story. I mean, there's a bit more, but this is basically the story for bounds on polytopes. So if that's what you have for general polytopes, because there's not really a lot you can touch in a general polytope, then you start asking, well, what do you do in special cases, right? So that's what we're going to look at now. So we're going to look at some sort of gradually more hard collection of polytopes where we can maybe say something about the diameter. So this part's very brief. We're going to just look at some network flow polytopes. What do I mean by network flow polytope? It's a polytope built on a network. And what do I mean by a network? I'm just talking about a directed graph. Okay. So I have a directed graph together with, at each node of the graph, I have a positive or negative value that corresponds to a supply or a demand amount. Okay. And then, so you just fix these numbers, right? You say you have this graph with these arrows, just like in the initial picture there, and then you have to assign some numbers to the edges, right? Called a flow, and so you should assign some non-negative value forward along each of the directed arcs, so that the sum of what enters and versus what leaves should be exactly what the supply or the demand asks for, right? So we'll see a quick example of this in a second. And the point is that every flow gives you a vector, right? It's a vector indexed by the edge set here. So it's a vector in e-dimensional space, and the collection of all of these such vectors is going to be a polyhedron. Right? All you have, after all, are these linear inequalities, and these are linear equations. And if you really care, all you have to do to make sure that you have a polytope and not a polyhedron is you just have to make sure you don't have any directed cycles. Okay, so the polytope is this, right? The associated polytope is the set of all of the flows, right?
You don't really restrict the number of sources and targets or something like that?
No, I mean, you just say, well, you have, the number of sources and the number of sinks is going to add up to cardinality of V. That's it. I mean, you don't say anything more. You can break down the parameters more, perhaps, maybe you can say something, but look, people haven't done that, that I know of. It's just, well, that's not quite true. That will happen in a second. But yeah, for the most part, it's just, well, we're just going to deal with these polytopes where the parameter is really just going to be cardinality of V and cardinality of E. And that's it.
Can I see the previous slide, Justin?
Yes.
So the second one, do you fix supply or demand at each vertex?
Yes, so you fix a number, right? You fix, basically to every vertex V, little v in capital V, you fix a value, like a B sub V or something, right? And the point is that this should equal B sub V. That's it. And the sign of this B tells you whether it's a supply or a demand. That's it. So maybe this is too many words for such a complicated thing. We'll see an example in a second. But I want to tell you some quick facts about them. The diameter is polynomial in the things that people care about, in the quantity people care about. So this is the dimension is at most, there should be cardinality symbols everywhere here, I think. Yeah, there should be. Anyway, the diameter of this polytope is actually going to be polynomial in the quantities people care about. Why is that? Well, it turns out that if you look at this polytope, you look at this, and you write out the matrix A of constraints for this polytope, you're going to only have ones and minus ones, right? Let me go back here, right? This ones minus ones, that's all you get. And it turns out that you have basically, if you write out what you have in each column, you're going to have at most 2 ones or minus ones. Right? And this is enough to say that this matrix is totally unimodular, or in other words, every submatrix, every square submatrix has determinant 0, 1, or minus 1. And Diane Fries proved in 2001 that such polytopes have diameter that's polynomial in the size of this constraint matrix. Okay. And more recently, Boniface et al. Proved that you can actually get this to be polynomial in just the number of columns of this matrix. Okay, so these network flow polytopes fit inside this framework. By the way, this 2001 result is something like m and n to the 19th power or something like this. And this current one is n to the 4th log n, or let's just say n to the 5th or something like that. Right? So this is it's a nice improvement. Network flow polytopes fit in maybe this framework of what people would call totally unimodular polytopes or something like this. But there's better bounds for this family, right? So that's the game. You have this just to sort of set some of the context, but the diameter is a little bit more than quadratic. Okay. There's some long series of papers. This is just some proper subset of the papers that tell you about this. Okay, so you can do a little bit better if you look at certain structure. This is sort of a bit of a toy example here, right? If you look at certain structure within the network you have, if it satisfies some kind of property that you start with a tournament and then you look at taking certain edges in some transitive way, so that if you have this dark edge in here, then you need to have all of these dashed edges as well. And if you have something like this, then you get that the diameter is going to be no more than 2 times e, where e is actually going to be the best bound that you can ask for if Hirsch would be true for this family of polytopes. Okay. By the way, why is it e? It's because the edges e were the only things that gave you inequalities, right? The inequalities were all, this edge has to have non-negative value. Those are the only inequalities. Inequalities are the only places you can possibly get a facet. Okay, so look, the annoying thing here is 2, right? If Hirsch is true, the diameter is at most e. And so what's that stupid 2 doing right there? Right? So this is a question we're going to keep coming back to. What is the stupid 2 doing there? Okay. All right. So what I want to do is now stop looking at network flow polytopes, but that's not quite true. We're going to still look at network flow polytopes. We're looking at very special network flow polytopes called classical transportation polytopes. What is a classical transportation polytope? This is an example of a classical transportation polytope. It is the flows associated to this network. Notice what you have you have some nodes which are supplies, you have some nodes which are demands, positive numbers, negative numbers, and if it's a supply, then it really only has outgoing edges and no incoming edges. That was allowed before. Right? Now if it has a positive number, it's only because it has outgoing arrows. And the similar statement for the negative numbers, right? if that's the case, you might as well have done what I've done here and just draw all of the supplies on the left and all the demands on the right and get rid of all the minus signs and the arrows, because you always have an arrow from each of the left ones to each of the right ones. This is all silly. Just remove all this stuff, and this is now going to be for us the same picture. Okay. Then a flow on this would be something like this. Right? So you can now go check that at every edge, at every vertex, you have that the sum of the incident edges, the values of the flows, you've summed them up and you get the value at that edge. Okay, so this is going to be, this flow then, I mean this vector will, there's a lot of zero coordinates as well, but this vector is going to give you one point inside the associated polytope. Okay, or to kind of make sure that we have this done correctly, we have a network flow polytope, which is a complete directed bipartite graph. And all the supplies are one of the vertex classes and all the demands are the other. Right? And so then we're looking at all the possible flows. Another way to say this is that you're looking at all of the matrices or the contingency tables. Right? All the matrices where the value of every row, the ith row adds up to some pre-specified value AI, and the value of every column adds up to some pre-specified value Bj. Right? To be very explicit, let's talk about 2 left nodes and 3 right nodes, or in other words, we're looking at all the 2 by 3 matrices with non-negative entries, where the first row adds up to 10, the second row adds up to 6, the middle column adds up to 5, and so on. And here's an example of a point that lives inside the polytope I'm trying to talk about. Right? Another example is if you have m and n are equal and all of the coordinates in A and B are the same, might as well just scale them to all be 1. Then you're talking about the well-known Birkhoff polytope, right, whose vertices happen to be the permutation matrices. Right, so every point then inside this Birkhoff polytope of size m is equal to n is going to be a convex combination of permutation matrices. Okay, so let's, it's a good thing I do have a board here. I'll just compute some quick things that should be easy from here, which is that this polytope, so if you have such a polytope, so this is a transportation polytope, it lives in an n by n dimensional space, right? So the ambient dimension is m times n. What is the dimension of the polytope? Well, let's compute what its codimension is, right? The codimension is going to be given by the number of equations you have, almost. So you have, every time you have a linear equation, you're cutting into an affine subspace, right? An affine hyperplane, in fact. And you keep intersecting many affine hyperplanes, in fact, m of them here and n of them over there. But actually, there's a redundancy between them, right? Any one of the equations could be recovered by the remaining one. So the codimension is actually m plus n minus 1. And so the dimension of the polytope is going to be mn minus this quantity. Right? It's mn minus m plus n minus 1. And if the Hughes conjecture is true, one other thing, I'm sorry. I need to know the number of facets. The number of facets is, at most, it's really the same question as earlier, right? So where do the facets come from? Inequalities. An inequality might not correspond to a facet, but that's the only that's the only place you can end up counting one. And the only inequalities you have are the non-negativity of every coordinate. So there's mn inequalities. This is an upper bound on the number of facets. Right? Okay, so summarize, the key things we want are the number of facets and the dimension, right? Number of facets, mn. dimension, Mn minus the quantity n plus n minus 1. So if the Hirsch conjecture, if Hirsch holds for these classical transportation polytopes, then the diameter should be at most number of facets minus dimension. So you take the number of, if the diameter is at most this, you raise that value up to this, Mn, and then you subtract this value, right? So you have Mn minus this quantity, the Mn's cancel out. So if Hirsch is true for transportation polytopes, then the diameter of an Mn n by n classical transportation polytope is going to be no more than whatever's in parentheses over there, n plus n minus 1. Okay, that's what that says. And you should note that if you prove an upper bound for classical transportation polytopes of m plus n minus 1, this is not proving the Hirsch conjecture for transportation polytopes. I mean, it's a really minor technical point. I wouldn't get hung up over this. It's just because this inequality might be strict, right? Nevertheless, sometimes this n plus n minus 1 is called the Hirsch bound, even though it doesn't really involve the number of facets. It kind of almost does, right? So let's just go ahead and do that. Everybody else does it anyway. And the point is that Brightwell, van den Heuvel, and Stelchi proved that the diameter of m by n transportation polytopes is no more than 8 times Hirsch. Okay, and this was improved recently by Cor-Herkens to 3 times Hirsch. Okay, so what I want to do is kind of tell you how you prove a diameter bound like this. But actually, before Brightwell et al. Proved this bound, they proved, I don't know, some constant times m plus n squared. So let's prove that. That's easy to prove. It'll kind of show us how to work through these kind of polytopes and how diameter bounds like this go. It's a good exercise. It'll make the rest of the talk make sense as well. So it's a good time to listen if you've been not doing that. So we're gonna prove that quadratic bound n plus n squared. How do you do this? Well, you can start by supposing that your polytope is simple. Right? This means that you generically perturb the facets, or in the case of transportation polytopes, you generically perturb the values of these vectors a and b. And what ends up happening is that every vertex is incident to only dimension many facets. It could only possibly increase the diameter of the graph of the polytopes you're dealing with. And luckily for transportation polytopes, what it does is, if you look at a vertex and you look at the graph of its support, you can think of it as a subgraph of the complete bipartite graph KMN, and the number of edges is going to be precisely n plus n minus 1 instead of something perhaps possibly less. So let's do this by example. I have to just assure you that I've picked numbers a and b here that guarantee that this is a simple polytope P. And I filled in the coordinates here so that you have a vertex. And if you take this and you draw over here in K4, 3, if you draw an edge for 1, 2, and for 2, 1, and 2, 3, and so on, you draw that, you get this, and you indeed see that you have exactly n plus n minus 1 edges, or it's equivalent to a couple other things. It means that you have that the graph ends up being a spanning tree. Okay, so every time you have a vertex and you draw the support graph, you get a tree that is where there is an edge incident to every vertex. And yeah, the converse is not quite true. Okay, and then so that's our combinatorial characterization for what a vertex is. Then what we need to do is say, well, then what's an edge, right? So maybe this is not the easiest way to say this, but you end up having an edge when you take 2 of these support graphs. So V and W are 2 vertices, right? So they both look something like this, and they end up being vertices of a common edge in the graph of the polytope if, when you superimpose or you union together the edge set, you get a unique cycle. There's a much better way to do this, and it is, I'll show you a better way to do this, and in fact it's sort of more simplex-like. You start at a vertex and then you ask, how do I get to another vertex? So let's just do that, right? That's a lot easier than thinking about what this really means, right? Let's just do stuff. So I'll do several things. I'll show you how that works. Right? So what this ugly sounding characterization of edges is, I'll show you how it works in practice, and at the same time prove this quadratic bound. Okay? So you take an arbitrary vertex like the one we just had, and you pick one edge. By edge, I don't mean necessarily an edge that's here, an edge of KMN. And for me, I'm just going to pick the 1, 1 edge, right? So that's an edge of KMN, this top one that's not there. And either in the vertex that you've picked, that edge is there or it isn't. Well, I want it to be there, so I'm going to just add it. Okay, so that's all I did. I mean, ignore the colors for a second. I just added an edge right here, and that's the only thing that happened in this picture. What did adding an edge do? It created a cycle. Why? Because you had a tree, you had a spanning tree. That meant that you could get from any vertex to any other vertex. But you add an edge, so now there's a new way to get somewhere, right? So you have this unique cycle. The length of the cycle is even because you had a bipartite graph. Right? So because it's even, it's well defined to go around and color all the edges blue, red, blue, red, blue, red. This cycle happens to have 3 blue edges, 3 red edges in alternation. And now what you do is you ask yourself the question, I want to subtract a certain value, call it epsilon, from every red edge, and I want to add a certain value, epsilon, to every blue edge. Why do that? Well, if I subtract epsilon from every red edge and add epsilon to every blue edge, then the net change at each node that's incident in the cycle is 0, right? Because you add epsilon here to 1 and you subtract epsilon away from 9, and you still get 10 here. Right? So as you do this process where I'm just going to subtract a certain value epsilon from every red, add epsilon to every blue, the same epsilon, you get another point inside the polytope. And you add and subtract until, and you go as far as you can, you end up traveling along an edge of the polytope until you get to a point where you cannot do this anymore. So there's a certain epsilon value that you cannot go past. And what is that value? If you choose epsilon to be bigger than 7, then you're doing 7 minus something bigger than 7, and you're going to get a strictly negative value. That's not allowed, right? Our edges have to take positive values. So that's the magic value of epsilon. That's kind of big for epsilon, I realize. But yeah, fine. Okay, you set epsilon to 7, and you change all the values. So all the blue numbers are going to become bigger by 7, including the 0 that's hidden up there. And all the red edges, you subtract 7 from them. So you have now this new edge that's zeroed out, so you delete this from the picture. This resulting flow is the support graph of an adjacent vertex. Okay, that was a lot. I mean, what did we do? Okay, well, I'm trying to do 2 things simultaneously, and I apologize for that. The first thing I'm trying to do is show you how pivots work. I think I've done that now. Now that you've seen how pivots work, I'm going to keep doing this, and now that we know how pivots work, we're going to use the pivots to try to obtain this n plus n squared bound. So how does this work? Well, what I did, I said earlier, I picked my favorite edge of KMN, which was, in my case, the top one. I added that in, and this is what happened, right? Basically, now what you always do is every time there's an edge of KMN that doesn't exist as an edge in the support graph, you can add it in and play the same game. So what I'm going to do is I'm going to look at the neighbors of the top left guy and the neighbors of the top right guy. Look at their neighbors. Here there's 1, 2, here there's 1, 2, 3. What I'm going to try to do is keep this one and remove the remaining ones. If I remove sufficiently many, something good happens. So how do I remove them? Well, as long as I still have them, I want to remove, right? So I want to keep this top guy, but I still have something else here that I maybe don't want, right? So I have this, and on the other side I have 3 total, but 1 I want to keep and 2 that I maybe want to get rid of. like this one, for example, right? So this is maybe one of the ones I want to get rid of. Right? It's not this top one. Okay, so I've highlighted two edges that exist here. And what you'll notice then is that you have this edge, you have these two other ones that we say now exist, and this edge here that's connecting what was incident to each of these, that cannot be an edge in the support graph. If it were an edge in the support graph, you would have a cycle of length 4. Right? And vertices are not allowed to have cycles in this support graph. Because it's not an edge, we can go ahead and add it if we want to do a simplex style pivot. So you add that, you have now a red, blue again, you update the values. Here, the smallest red value is 2, so epsilon is 2. You add 2 here, so you get 9. You get 2 here, you get 0 there, you get 5 minus 2 there, 3, right? So you update all the values and you get this. Okay, what did that do? That removed one of these two edges. This one, right? That's good. Our goal was to remove these edges. So you keep playing this game. You still have this red one. You still have another one down here. You can, again, this edge was not, let me go back. You have this one, so this edge can't exist because there are no cycles yet. So you go ahead and add that to make a cycle, and you do your pivot on this edge. That's what we call it. We do a pivot on the 3, 2 edge. So you do this again, and it's going to zero out now one of these red ones. The point is, this top one always stays blue, meaning the value increases, meaning the edge cannot go away. The red ones are the ones that are incident. Those are the bad ones, and one of those two are going to go away. And once enough of these red ones go away, either this side or this side is going to become a node with degree 1. It'll become a leaf. When we have a leaf, in what we started with some initial vertex, we have a leaf, we stop. So we did this to one vertex, we do the same thing to another arbitrary vertex, and we get the same leaf over here. Okay, you have to work through why that's true. You get the same leaf, but then you can just delete this. You delete this from the picture in both, you started with X and you came to here, you start with some other vertex Y, you have its support graph, and you do this, and you get, I don't know what the rest of it looks like, but this part is going to be the same, and you remove the same thing there. And then by induction, you continue. Okay? So what happens? You get a common leaf in how many steps? Well, you might have to do number of total edges there are in here steps. Right? So you have to do number of edges total in here to get a common leaf, and then you have to do the same thing in Y. So you should get twice number of edges, number of total edges. So in at most, twice the total number of edges there are, you're going to get a common leaf. Right? So this is this kappa value here. This is it. And then all you do is, you need how many common leaves? The number of edges there are. So you take this thing and you multiply by number of edges, which ends up being the dimension, actually, if you go back and compute. Or if you want, it's the number of edges in KMN. So the diameter you get is basically going to be kappa times number of edges. That's the upper bound. Okay, so now you see where this bound of n plus n squared comes from. Yeah, there's a factor of, 4 in front of it, right? Because you had to do this for x and you have to do this for y. The point is that Brightwell et al. Showed that you don't have to do it this way. You can pick not just the one edge, but you can pick maybe another edge in some nice way. And when you do that, you can ensure that, so how did they prove something like this? They proved that you can always get a common leaf in at most 8 steps. Right? So now here, it takes some work, but the kappa here that gets you magically what you want doesn't have to depend on m and n. Okay? And then finally, Herkins more recently proved this, right? This 3 times Hirschbound. And how do you do this? Well, nobody yet knows how to get a common leaf in kappa's 3 steps, but he knows how to get S common leaves in kappa times S steps. And so this is good enough to get what you want. Okay, so we don't see how these proofs exactly work, but you get the picture of what kind of things you need to do. Right? You just have to pick your initial, instead of picking 1 as your favorite all the time, you have to pick your favorite better each time. And I mean, if you do that, then you get this. Okay, so this is sort of the best bound that's known for classical transportation polytopes in general. So then you can ask, well, what about special classes of them? And I'm going to run through some of these. I'll skip some details. But the Hirsch conjecture, and this time actually the Hirsch conjecture is true for 2 by n classical transportation polytopes, whose supports, if you draw them in this table fashion up to reordering the columns, are going to always look like this. And together with Henning and Vincent, we proved that that the Hirsch conjecture is true for an m by m plus 1 generalized Birkhoff polytope. And actually, a larger class of polytopes that I would rather not detail at the moment. So what I want to do is, I want to skip some. I mean, I'll put these slides online or give them to you if you email me or whatever. But okay, so there's a reason I want to skip this proof for the 2 by n polytopes, and I just want to comment that there's some sort of, I'll just comment on one thing in the proof. There's a certain rotation that occurs. So you take the 2 by n classical transportation polytope you can note that it actually is a certain subset of a cube of a particular dimension. Because you have a cube, you can actually do some rotation to make sure that you've sort of positioned the 2 arbitrary vertices you have to be where you want them to be. At least one of them is where you want it to be, and then you kind of, relative to that, the other is more or less where you want it to be. But the point is that this proof is sort of cheating because you have to know where both of the vertices are to do this thing that you're doing. But in the end, you get a Hirsch bound, and the reason, I'll say a little bit more about this in a second. The reason is that you start at some initial vertex, and you're not just trying to do something like we saw in the previous proof where you try to generate a common leaf in both x and y. You take x and you take x and you take y, you rotate, which doesn't change the number of pivots, right? It just sort of, it's your cheat to make sure that you have the setup the way you want. And then you start doing pivots from x to y where you're sort of sensitive to what y's support looks like. That's the only key point I want to draw. And you have to do that in order to get a bound where you're not going to have that 2 in front. Okay, that's I don't want to say too much about this. I'm going to sort of say this again right here. How things go right now, right? For basically all the diameter bounds for transportation polytopes that I know, how they go is you take 2 vertices, x and y. Let's imagine this is your transportation polytope, the graph of your transportation polytope. What you do is, you start at some vertex x. You have to pick 2 arbitrary vertices, right? X and y. So maybe you pick x, and then you have some. You specify. Your proof specifies an algorithm that gets you from x to some magic other vertex, right? Some hub, call it z, right? And then you take your other arbitrary vertex that you've chosen, like maybe this one is y, and then you go from there, your algorithm again, you just run the same algorithm on that vertex, and it gets you to some other vertex, to the same, common hub vertex. And the point is, all your algorithm does is it looks at x and it does something, and it looks at y and it does the same thing, and it doesn't care about what they look like together, when you could be doing sort of silly things like this, when maybe you should just find some other path. I mean, of course the question is how do you find such paths, but if you do something like go to a common hub, I mean, this might not necessarily be true, but maybe morally speaking, you shouldn't hope for a bound that's better than twice Hirsch, or twice whatever the true bound is. I mean, there's no reason that has to be like this, but I mean, it is a little wasteful, right? So this is the point, is that this is sort of some some take-home message. Like maybe, can we do something where we consider something about the combinatorial relationship between the two arbitrary vertices that we start with? Okay, that's the question. And the point is, yes, we can do this if you look at generalized Birkhoff polytopes and some generalizations of these too. So what is a generalized Birkhoff polytope? We saw a Birkhoff polytope, right? Where you have M and N are the same, and the values of the supply and demand vectors A and B should be constant. It's the same story here, but now M and N are not the same. Okay? So for example, I think you see in this picture a 6 by 7 generalized Birkhoff polytope. Okay, so this is a special classical transportation polytope. If the values here have to all be the same, and the values here all need to match each other, then you really need to pick these numbers or some scaled version of this. The reason is that these numbers are subtotals of values over here, and these are subtotals of values over here, so therefore the sum of these better add up to the sum of those, and you might as well just pick these numbers. All M's and all N's. Okay? I mean, anything else you do is just going to be a scaled version of this anyway. It has to be that if all the numbers you pick are going to be the same. So we look at generalized Birkhoff polytopes, and we prove that the Hirsch conjecture holds for these and something for some other general class. And I realize that the proof, which is again specifying some algorithm to get from x to y, is a bit complicated. So I want to illustrate the most important thing, which is how it might work on an example. What ends up happening in these polytopes is that whenever you look at a vertex in a generalized Birkhoff polytope of size m plus n plus 1, n by n plus 1, you look at any vertex and you look at that support graph, right? It's a subgraph of the complete bipartite graph on m and m plus 1 nodes. In that graph, the supply, or every left node, is going to have degree exactly 2. Right? So I don't know what it looks like over here. You may have things that have degree 1 and 3 and whatever, but here you always have these v's over here. Okay? And what that means is that, let's say you have this demand guy over here, and maybe there's no edge from this one to this, but if you add this in, it's going to create a cycle, right? It creates a cycle. The added in edge is not going to be the one that goes away. Then some other edge somewhere goes away, generally speaking. But and that edge that goes away is one of those ones that are labeled in red. Normally that one that goes away is somewhere far away, but because here you have this constant degree condition, the edge that goes away is going to be the other edge incident to this node that's in the cycle. Okay, so how does this work on the support graph of two vertices? So we pick two arbitrary vertices, x and y. Here they're support graphs. Right? These are the support graphs of two honest vertices inside the 2 by 3 generalized Birkhoff polytope. Just to illustrate how this works. What you do then is you start at a leaf here and you identify an edge, okay, that's incident, and then you pivot on that in the other vertex, okay, and what that ends up doing is it's going to delete. So you have the cycle, and I don't even need to tell you what the numbers are here. You could go back and compute them easily, but it's like I said from the corollary we just saw. It's clear what has to happen. You have the cycle. This edge was added. And here's the cycle. The red edges are this one and this one. So the one that goes away cannot be this one, because if you took away that one, the degree of this thing would grow. Right? And we can't have a degree 3 here. It still needs to be degree 2, so the one that goes away has to be this downward sloping edge. Okay, so we get rid of that. Then what we do is, now we start over here. So we go back to the original vertex. We follow along and we sort of continue the length of this path. And we add this edge in. That's right. So we That's what we do. I'm sorry. So we've added this edge in, then we see what is adjacent to this, right? There's a unique other edge over here. We pivot on that in the other one. Basically, we swap the role of x and y. And over here, again, we can say with confidence which edge is going to go away, right? Inside the cycle, it's got to be the other edge that's not blue that's incident to this. Okay, so the 1, 2 edge goes away. Okay, so I put this in red. Notice that the 1, 2 edge goes away here. And we do the same thing again, right? We follow along the path. We add this edge in on the other vertex. We know which edge goes away. And at this point, we got lucky that we don't have to go any further, right? Sometimes you have to keep doing these steps, but at this point, you can actually trace the paths and see you actually have the same vertex now. One of the key things, if I can go back, was that when we started this process, the 1, 2 edge went away in one of these, and we did something, and then the 1, 2 edge in the other guy went away. And this was sort of labeled as something that was bad. This was sort of supposed to be the problem child transportation polytope in the Brightwell et al. Paper. They said that this is no good, and that you have the same edge go away. Because then what you don't have, then you don't have this lovely property which they had hoped you would have, which is you start with 2 vertices and you hope that you can pivot from one to another or the other to the other or whatever. You want to do pivots in such a way that the number of edges that are in common would keep increasing. And that doesn't happen with, I mean, it doesn't matter if you do the series of pivots I told you or what. I mean, you can look at all the ways you can pivot from here to get to here, and you will always, at some point, in some way along the path, you will not increase the number of edges that are in common, because this will give you a Hirschbound right away. But you can't do that, and that's what this highlight in red thing does. But the key thing we noted is that maybe you don't want to keep track of the number of edges that are in common. Maybe what you want to do is keep track of some collection of edges which are in common. So we've highlighted in blue, right, these things that we're going to keep, and then we do this, and then we're going to keep this one over here. I mean, every time, there are already edges that were in common, like this one that's labeled in black that we haven't touched at all. But the point is we're not going to start by accounting for all of the edges that are in common, but maybe look at just some part of this and build that slowly. So I want to summarize what made the last, I'll be the first to admit to you, it's not a large enough class of polytopes, but it's interesting for this, that what we do is, the whole idea is you take 2 vertices, x and y, and you go to some hub. And now what we want to do is use the support between x and y, I mean, use the combinatorics, that the relationship between them, to try to go from x to something else and from y to something else, and sort of keep meeting in the middle. Right? And the point is that we believe that what we're doing is doing this in a way that's not blind to the similarity between x and y. And the other thing was, I mean, the old comments were the cautions were something like, we can't seem to do any better with our bounds because we're looking at the set D, which is the collection of edges which are in common, and we can't seem to keep increasing the cardinality of D all the time. But maybe it's important to consider some subset of D, right? So like some set C, like as we have kept labeling in blue in the edges you saw in the previous slide. So those are some of the ideas that we want. And I want to quickly mention that there's more recently a class of polytopes as well, sort of similar to ours, but still a little bit different, where now the value of the A vector is all 1s, and then the B vector can be anything. And for I mean, this is a lot to read, but Hirsch holds for this class. This was recently proved by Borgvard. I just need to mention that to make sure I've said this. I want to now I want to take these ideas and quickly briefly discuss another problem: 3-way transportation polytopes. So I want to look at what we've seen so far, what I may have kept calling transportation polytopes, and look at some sort of variant of these things, where now you don't have entries x sub ij, but maybe you have now entries that live inside a three-dimensional thing, like inside the Rubik's Cube, right? Each square block of a Rubik's Cube will correspond to a coordinate of the polytope. So now I'm going to pick three vectors, A, B, and C. They're sort of pictorially given here, right? A could be these numbers, B are these, and C is these. And I think you're already seeing what I want to do. This is the thing that's analogous to the matrix or the table I had earlier, right? It's just now that I want to add up everything along some slice and say that it has some certain constant value. Otherwise, it's sort of the same story. I just have my coordinates are now indexed as x sub ijk's, right? And I just ask that everything in certain slices add up to something. So everything in this left slice should add up to 112. That's probably what A1 is. A2 is 18 and A3 is 30, and you do the same thing for slices in this way, like front slice, middle slice, back slice, and then again with the levels, right? So you slice in all the possible ways, and you get a polytope out of this as well. You do the same kind of calculation you do here for bounding the number of facets and dimension, and if the Hirsch conjecture is true for this class of polytopes, this class of three-way transportation polytopes of size L by M by N, then the diameter should be no more than L plus M plus N minus 2. Okay, it's the same computation as before. And these polytopes are relevant because if you take any rational polytope, any bounded polytope, rational coordinates, then there is a polytope of this kind whose face is combinatorially equivalent to your polytope. Whose face? Yes, a face. Is a face. Oh. Yeah, that's so. So you pick your favorite polytope, P, and then I will find one of my polytopes I just defined and tell you about a face of it, which is basically given by saying which coordinates are forced to be 0, and that face F is going to be isomorphic to your polytope P. It's a face of my polytope Q, and that face is your polytope P. Okay? Unfortunately, the diameters of faces don't tell us about the diameters of the whole polytope, not in the way we want. The relation goes the other way around, so that's the only sad thing here. But we have this 2 times Hirsch squared bound here. So how do you prove a bound like this? Well, let's do it. So you do some kind of induction, or let me just say it this way. I'll just describe the algorithm. Right? So what you do is you look at the support. Again, before the support was you look at some edges that correspond to strictly positive entries in the graph KMN. And now what you do is your support all lives inside a box. Right? You have a bunch of sugar cubes that sit inside the sugar cube package. And now, what's the one, and that top edge I picked before, that favorite one, I'll just pick the corner one. This is the 111 entry now, right? And we'll play the same thing as before, which is that before we had, we wanted to add the 1, edge in, and here you add the 111 cube in. That's no problem. You just do it. Some other edge went away, so some other cube somewhere in here goes away. Then we have these annoying suckers, right? We wanted to remove them. What do these things correspond to here? Those are, maybe these ones are entries that other times where you have a strictly positive entry somewhere in this top layer. And these are in, this way. Well, now you have a third direction too. So you want to avoid entries in this thin top layer, or this rightmost thin layer, or this leftmost thin layer. Right? So if you can avoid having entries in there, you're good. So let's prove the quadratic bound. So you run a while loop. While you still have entries in here, here, or here, you need to get rid of them. So there's several cases. Let's just do the easiest one. Let's say you have, you have this one, and one way that you could have you stop when one of these 3 slices are empty, except for this entry, right? Which you want to keep this entry always. So one way that all three slices could still have support entries is maybe you have one that's common to this slice and to this slice. Maybe over here. And then maybe you have one somewhere in the interior, this one over here. Then what you do is you draw the rectangular prism that has some entry somewhere really deep in the middle of this rectangular prism. That entry, if this entry is positive, this one and this one, this entry has to be 0 because otherwise you'd have a cycle. Right? So then you go ahead and pivot on that. And you add to this entry, you add to this entry, in particular it doesn't go away. You subtract from this entry and this entry until one of them shrinks down to 0. And that's what you wanted. You wanted to get rid of either this one or that one. And there's some other combinatorial cases you work through, but the point is that there's a way to do it every time in at most 2 pivots. And so that ends up giving you certain combinatorial local properties on the graph, and say take some subset of these properties at a time and then try to prove some kind of bounds on the diameters of this larger class of graphs. And so some people, Eisenbreit et al., have proved an almost quadratic bound if you satisfy one combinatorial property. And this is sort of maybe the most important property, and then separately I looked at, well, what if you have properties B and C instead and not A, whatever these properties are. And then you can still get some bound. Right? It's not, the question here is not which bound is better. It's really, in the end, the ultimate goal is combining all the properties and getting something that's more than linear, so that you have perhaps an approach to disprove the linear Hirsch conjecture. I mean, still there's a question of whether the graphs you have are going to be realizable as graphs of polytopes and all this kind of thing. And this kind of statement, there's an analogous thing for transportation polytopes as well. So what have we done? We've looked a bit at the original Hirsch conjecture, and we looked at a special class of real polytopes and tried to say what we could about diameters. And we looked at sort of what people are trying to do a little bit more in the broader sense of looking at some things that are more than polytopes to say something about diameters. What's left for transportation polytopes? There's this Hirsch conjecture for 2 by n, so now how about 3 by n? It turns out you get an awful number of cases to work through for the kinds of pivots you need to do. The next thing you could do is maybe, so I mean it's still interesting to solve, because if we can't solve the Hirsch conjecture for this, or even maybe twice Hirsch for this family, how do you hope to do it for n by n transportation polytopes? You can ask for maybe the easiest case of 3-way transportation polytopes to look at, and I would say that they're going to be the 2 by 3 by n ones. And I mean, if we could get a bound that's linear in one of these quantities in just n, that would still be good. The way to attack this is to combine several ideas. One is the one of Cor-Herkins, where he got several leaves simultaneously, so you have to pick the right favorite corner. It doesn't have to be the 1, 1, 1 entry, right? You have to pick one correctly, and then from picking that one, you have to make sure that you can get S leaves in a certain constant number of steps. The reason why this is the right family to look at is if you can reduce this by 1, then you're really looking at 3 by n classical transportation polytopes. If you can reduce this 3 down by 1 to 2, 2 by 2 by n polytopes of this kind happen to be 2 by n classical transportation polytopes. And finally, I think you have to use a structure of x and y together somehow. Sort of looking further than transportation polytopes, then we can ask, I mean, these are more lofty things, right? Just prove the Hirsch conjecture sort of generally for n by n transportation polytopes. I'm not even sure I believe this is true anymore. Now I've said this on video. And then, well, the analogous question for L by n 3-way transportation polytopes. And then, finally, with that, perhaps that last approach or something else, what about the linear Hirsch conjecture for polytopes in general, or for transportation polytopes for that matter? I think those are all the things I wanted to say. A couple minutes over, sorry, and thank you.